some of the requirements earlier on before moving to materials that are researched for organic light emitting diode applications. So, okay, it's stuck. So OPV we talked about, and recalling that you need a donor acceptor kind of material heterojunction in an OPV cell to make it work. And the process of working involves formation of exciton and separation of the charge carriers. So dissociation of the exciton is the basic principle. For organic LED, the reverse is true. You are supplying charge carriers from an external source, and you're trying to make exciton, and the recombination of the electron and hole is responsible for the generation of the light. So on the left-hand side, you see the simplest design of an organic light emitting diode. There are much more complicated designs which we'll look a little bit later. But the simplest design includes an emitting layer or organic electroluminescent layer, which is the material that is responsible for the acceptance of the charge carriers and allowing the charge carriers to recombine, electron and hole in the colloquial sense, not exact sense, because we don't know if the emitting layer is a polymer or a small molecule. In polymer, charge carriers are a little bit complicated. So in the emission layer, which forms the bulk of the OLED, you have the recombination of electron and holes that leads to generation of light. The electron and hole have to come from an anode and a cathode. On the anode side, usually you have a glass substrate coated with indium tin oxide. Indium tin oxide is coating on glass, is conducting in nature and transparent. So that acts as an anode or a source of hole that gets injected into the emission layer. You have the cathode side, which is usually a metal that is opaque and usually reflective. That supplies the electron from the external load. So that acts as the cathode. And then you may have a substrate that is flexible in nature, either a glass or polyethylene terephthalate or any other material that is transparent to the light you are trying to emit. So it doesn't have to be transparent to everything. It just has to be transparent to the light you're trying to generate. So those are the basic components of a LED. But of course, in a minute, we'll find out that there are more. It is not this simple. There is a little bit more of a complication to it. First, the material requirements is studied in research laboratories by making a device like this, applying a voltage, and studying its current versus voltage curves to study different things such as luminescence, how much light is being generated, what color of light is being generated, and how efficient the device is. So for that, these kind of experiments are done. You set up a device and measure the current versus voltage characteristics. Very similar to any semiconductor device. When you study semiconductors, of course, you study IV curves. In addition to current and voltage, you also study luminescence, which represents how much intensity of light, how bright the light is. Generally, if you construct the device correctly, the current versus voltage looks something like this, and luminescence and current density usually have a strong correlation with each other. Current density is going up and luminescence is going up in step to it. Of course, this is they are matching in the scale because they increase in the same voltage range, but on the y-axis, the curves match perfectly because of the choice of axis. But nonetheless, you can see, at least visually, looking at the IV curve, that luminescence and current density have strong correlation. What does that mean? That means that things like charge carrier mobility is important because that um, is correlated with the current density of the full device. As for the color, we know that color is dependent on the band gap. So band gap and charge carrier mobility, just like the previous devices we talked about, are important in this case as well. Which means you can pick and choose the emission layer to try to enhance these properties such as band gap, which modulates the color, and mobility of the charge carriers, which dictates how much luminescence you can achieve. And this is how you study in a laboratory setting by doing this IVL curve experiment. So this is kind of self-explanatory note of what I just mentioned. The efficiency of organic LEDs are dependent on several factors, and people who study organic LEDs also study the efficiency of these devices. Efficiency would be how good the device is at using electrical energy for generation of the light. And the overall efficiency of the device depends on factors such as what fraction of holes and electrons get into the device and combine, what fraction of those combination gives rise to singlet excitons that emit through radiation, and that is the fraction of excitons that are capable of emitting. Then there is a factor called the probability of radiation decay. So the first factor dictates how good the device is at injecting the holes and electrons into the device and how good the material is to allow for the recombination of electron and holes. So that is one factor. The other factor is what fraction of the electrons and hole combine. They combine to form excitons, and what fraction of that are able to emit radiatively. When coming to charge carrier recombination, there are non-radiative processes as well. So there can be events of combination of electron and holes that do not give rise to radiation. And that's why you have this factor, which is a fraction. It is not going to be one. It's not going to be perfectly one. And what fraction of that further is actually emitting radiation. Singlet excitons with singlet spin, give rise to fluorescence, and that is the basic process of emission in this kind of setup. So normally in simpler devices, you would generate the light through the fluorescence process, and since all combination do not give rise to singlet excitons, this factor is less than 1. So looking at few numbers, this factor can be close to 1, but not going to be perfect. This factor, second factor, is also going to be close to 1, but not always going to be perfect. The chi value, if we are limiting the discussions to the fluorescence phenomena, has the maximum value of 1/4, as long as we are limiting the discussion to fluorescence emission processes. If you have other phenomena that give rise to light, then this factor can go up. But the bare minimum an LED which works to the fluorescence phenomena has to have the chi value close to 1/4. The external efficiency that I didn't mention is a factor that tells us what fraction of the emitted photons, because exciton radiative recombination gives rise to photons, what fraction of those photons escape the device. That needs to be accounted for. Because this is after all a real life device, you can imagine that some photons will not escape and will get uh, uh, combined. They will not escape the device and stay within the device. Because of that, that factor needs to be taken care of. In some textbooks, they use this formula, 1 by 2 n square, where n is the refractive index. That assumption or formula is based on the fact that we are looking at a device that is a cuboidal shaped device. So that's based on that. So some textbooks use that formula. So overall, the maximum efficiency of a simple fluorescent OLED has this maximum limit, which means you want this factors, the first two factors, to be as close to 1 as possible, and that is already achieved by the people who work in this field. That factor is not too difficult to be very close to 1. The third factor will come back to it. If we introduce non-fluorescent radiative processes, this factor can go up. So that will come back to it. And this one is, of course, limited to a near perfect device will have this factor as 1 by 2, because refractive index cannot go below 1. This kind of the meaning of refractive index, as long as the material, we are talking about materials, not vacuum, and has to be greater than 1. So that is the upper limit for this factor. So the upper limit would be how much? 1 by 4 by 1 by 2, so 1 by 8. So efficiency of fluorescent organic LED in this kind of device cannot go above 1 by 8, which is what, like about 12.5% efficiency, which means the absolute maximum limit for a fluorescent OLED would be 12.5%, which means it is going to use 12.5% of the electric energy to generate the light. That is, of course, for fluorescence, and we'll talk about other kinds of radiative processes. For those who are familiar with it already, you know that the other radiative process would be phosphorescence. But we'll look at simple fluorescent devices first before moving on to them. Material requirements for all the components. Oh, by the way, I missed something. This N or refractive index refers to the refractive index of the whole system as a whole, not just of any single component. So that may be a source of confusion. So it's talking about refractive index of the whole thing. But since the emission layer is usually the largest or thickest layer, it can be close to the refractive index of that material. The material requirements for the devices individually should be such that it has to have high luminescence quantumly in solid state, which means this factor has to be as high as possible. The charge carrier mobility, doesn't matter if you're talking about P-type material, P-doped material, or N-doped material, has to be high. The term high is a relative term, of course. These kind of values are achievable in modern OLEDs. But of course, since we're dealing with organic material, by their very nature, the charge carrier mobility is going to be on the lower side compared to traditional semiconductors. So just giving you a flavor of what the range of mobility is. Perhaps a traditional semiconductor OLED would have much higher charge carrier mobility. Something that is important is the material, the emission layer should be able to form films quite readily, and it should be stable as well. So those kind of things are factors. one small factor that comes into play in organic LEDs is what is called vividness or color purity. So it is kind of difficult to describe color purity without having to deal with a lot of maths. So a color purity is how blue is a blue or how green is a green. So how much yellow is a yellow. So orange is not exactly yellow. So the yellowness of color orange is very far off. Similarly, comparing blue and green, something like violet is not exactly blue. So the blueness of violet color is very poor. So on a scale of 0 to 1, the primary colors can have a vividness scale. A scale of 1 is a perfect blue color, and scale of 0 would be white color. So those kind of color purity in the device is also important, because people like to have single colored LEDs for display applications, because displays make use of pixels that are the primary colors, and the purpose of making LEDs, apart from general lighting, is to have display technology. So people like to have LEDs that have high color purity. So that factor comes into importance in LED, which never was a factor in other kinds of devices. Oh, yeah. So white or black. 100% color if there is no white. It's meant to be no white or black mixed into it. Organic LED field has two types that is studied: small molecule based and polymer based. And polymer based ones can be conjugated and non-conjugated type. Why that is so, we'll look at examples a little bit later. Small molecules are easier to deposit through evaporation techniques, like vapor deposition techniques. So you vaporize under vacuum and deposit on a cooler film. For polymers, you deposit by spin coating. For small molecules, you can use screen printing methods to have more complicated layered structures. While polymers, it is a little bit difficult to get complicated structures, but polymers are good at very fast deposition, which allows for printing through inkjet printing or roll-to-roll printing, so faster fabrication. Small molecule, on the other hand, if you want to make more complicated structures, that can be useful. One example where complicated deposition for small molecule emissive layers is relevant is when making white color LEDs, and we'll look at that later. We can deposit 3 different colors in 3 different stacks, and when light emits from them, the mixing of the colors can lead to formation of white light. So those need little complicated architecture, which are achievable by small molecule organic LEDs. So we'll look at one design. Will not take too much time. We'll look at one simpler design of organic LEDs that was studied, and one complicated design. We'll talk about that. We'll not talk about all the intermediate designs that people have studied. So the earliest design for a small molecule organic LED is shown like this. You have a glass substrate. Earlier on, glass was convenient because deposition of indium tin oxide is a lot easier on a glass substrate. So you have the anode set up, usually a transparent anode. Then you layer in a diamine material. This is an example for diamine, N and N, 2 amines. And that is called a hole transport layer, and that modulates the mobility of the hole and electrons. Since These are small molecule devices. You can see already the emissive layer is a small molecule. The electron and holes have different mobility. And since the basis of formation of light is recombination of electron and hole in the right place, you need to control their mobility so that they recombine in the right place in the device. You don't want it to recombine in the anode or cathode because that will not lead to efficient process. That's why from the very beginning, people have started using layers called the hole transport layer. Then you have the main emissive layer, which is a fluorescent molecule, and it can be deposited through vacuum deposition. And we'll talk about color a little bit later. So this is an organometallic complex, aluminum complex. We'll just call it ALQ3. Its full name is going to be too long. So this is aluminum bonded to phenol-like groups of a quinoline-like system where nitrogen is stabilizing the complex. So these kind of structures on a 3D are centrosymmetric. So it has a point of symmetry. Let me think. Is it a point or is it a plane? I think it is a plane of symmetry. I'm having difficulty imagining 3D. But it has a center of symmetry at least. So these molecules are used in the earliest design of OLEDs. The way to deposit is that you have different types of ALQ3 material. You have a mask and a substrate, and you're spinning the substrate and putting the whole thing in a vacuum chamber and heating the small molecule ALQ3 compound. And ALQ3 vaporizes and gets deposited based on the position of the mask. That's how you deposit ALQ3 onto a substrate by vacuum deposition. The diamine, which is controlling the charge carrier mobility, is based on the fact that nitrogen with benzene ring next to it are good at stabilizing radical cations, which assist in transfer of holes. Not as much for electrons. That's why they have a differential mobility of electron and hole in the hole transport layer. And then you have a metal cathode, which completes the device. And when you apply a current to it, if the design thickness is appropriate and if the choice of diamine hole transport layer is correct, you will have a formation of exciton and then recombination to generate fluorescent light from the ALQ3 layer. So this ALQ3 is quite different from the molecules we have seen before. That is because it has to have these kind of properties and has to be fluorescent molecule. So the earlier small molecule OLEDs had this kind of unusual molecule. You can modulate the color of the LED by modulating what the ALQ3 complex is made out of. There are a variety of molecules that are derivatives of the traditional ALQ3. You can put different aromatic groups conjugated to the quinoline rings, and that will modulate the band gap as well as the color. So we can have a series of electron deficient systems stuck to the quinoline ring by an alkyne bond, and you can have electron rich systems, and based on that you will have different band gaps. If you recall, electron donating groups raise the energy of HOMO, and that's why going from A to K, the energy of HOMO is going up while LUMO is not getting affected too much, and that changes the band gap, and that in turn changes the color you would expect from the device you make. So effectively, by choosing what the RL group is, you can have a variety of band gaps and therefore a variety of colors. So you can have the conjugation separated out by a triple bond, or you can directly connect it as well. So many varieties of ALQ derivatives have been studied for their ability to form or emit light of different colors. So these are in solution, these are in solid state for this family of structures. I'm not showing all the colors, but showing that going from A, you go through K, you are getting the red shifting of the device. You start out with bluish to reddish color. And you can do that in solution. These are cuvettes in which you have solutions of these molecules, and these are substrates, the compounds deposited on a substrate. So you can get a variety of colors out of it by correctly choosing or appropriately choosing the side groups. And all of the compounds are fluorescent compounds. Since the earlier devices, which was studied in 60s to 80s, there have been more and more complicated designs of organic LEDs. So the one we talked about was already studied in 1980s, and since then more and more complicated devices have been studied. And in those complicated devices, you have things like whole transport layer, p-doped whole transport layer, electron mobility controlling layers, electron transport layers, doped electron transport layers. So many small variation in different kinds of material that you can layer in and control the thickness of the layers as well to have more and more efficient usage of the electrical energy to generate light. We can't really talk about all of the intermediate design. We'll just look at one example of a slightly efficient OLED, and more specifically an example of a phosphorescent OLED. So this is a basic design. There are many layers. We'll talk about them individually. Some of them are quite easy to understand. The glass substrate is, of course, to have a transparent, stable support onto which you can have the anode, indium tin oxide anode deposited. Then you have this alpha NPD, that is the whole transport amine that we talked about. We'll more on that in a minute, how it looks like. Then you have an emission layer, which has a host molecule and an iridium complex, no longer an aluminum complex, but an iridium complex. More on that in a minute. You have an exciton blocking layer, which controls the transport of exciton. You still have ALQ3, phosphorescent molecule, and also it acts as a controlling the transport of electrons. You have the cathode on the other side and a layer of lithium fluoride that modulates the work function of the aluminum, so that all the band structure and all the HOMOs and LUMOs of all the layers are just balanced, so that there is no or very little barrier to the injection of holes and electrons. And by that I mean the source of electron and hole is the external power source, and the combination of the electron and hole and formation of exciton and emission is happening in the emission layer. But you need all the other layers to control the mobility of charge carriers, so that you get as perfect of a recombination as you can. So many layers modulating the mobility and increasing the probability of the radiative process from happening. Why iridium? Because both aluminum complex and iridium complexes are centrosymmetric, and centrosymmetric material do not allow phosphorescence phenomena. And phosphorescence phenomena happens when you have a triplet energy state that has a certain population of charge carriers, and decay of that leads to phosphorescence instead of normal singlet to singlet decay that gives rise to fluorescence. So compounds that are centrosymmetric, like aluminum complex, which means they have a center of symmetry, or other symmetry elements apart from the center of symmetry. In those kind of molecules, triplet to singlet transition is forbidden. And by forbidden means even if it happens, it is not going to be able to generate radiation. But iridium, although structurally, crystal structure wise speaking, it is still centrosymmetric, but it has empty d orbitals. And for the chemists, you know that that's a simple joke. If you have a transition metal, you can answer any questions related to transition metal by saying that it has empty d orbitals. That is also true here. When you have d orbitals, that prohibited triplet to singlet transition is allowed because even though the atoms, the arrangement of atoms is centrosymmetric, the empty d orbitals break that symmetry and that allow for the phosphorescence phenomena to happen. And because of that, the sky factor can now go above 1 by 4, which was limited to 1 by 4 for fluorescent compounds. So the emission layer has this iridium complex that allows for both fluorescence and phosphorescence phenomena to happen, which increase the efficiency of the whole device. Usually this iridium complex, you just do not directly deposit onto the layers. You have to have a host molecule, and host molecule is usually another diamine or certain sort of an amine that on in itself acts as a host to have a uniform distribution of the iridium complex, but also by itself controls the mobility of the hole. So this is one example of a host molecule that is an amine. Here also you can see that this amine with benzene things next to it. So those kind of molecules are good for this kind of application. Instead of whole transport layer, you can have electron transport layer as the host material, but that will require another kind of emission layer and or other kinds of layers that makes the system complicated. Those complicated designs exist, but will not go there. Will limit to a host that controls the transport of holes and also acts as a host for the iridium complex. And that forms this layer, which is the main layer from which the exciton combination and emission is happening. Yeah, this is pretty much the repetition of what I said and just written down in a more complicated manner. Let's skip that because it's going to take a little bit too long. The summary is the emitter has this really big molecule atom, and that has empty d orbital, and that allows for triplet to singlet transition, and that allows for phosphorescence. More chemistry details if you want, you can read about it. Exciton blocking layer. So this layer for this particular design, these are these unusual molecules with lots and lots of fluorine. It's pretty much a bunch of aromatic rings with all the hydrogens replaced with fluorine. These are called perfluoro compounds, and more specifically perfluorophenylene compounds. And they have the correct Luhmann HOMO that allows for modulating the transfer of electrons. They block hole more than they block electrons effectively. So effectively, when the electron and hole are formed and you are blocking the hole more than the electron in this exciton block layer, it is giving the electron and hole more of an opportunity to make an exciton. So it is modulating. Otherwise, the hole might escape to the negative side too quickly. So that's what it is doing by making a barrier and controlling the transfer of holes, and that allows for a higher lifetime for the exciton. And when that happens, the chances of radiative combination is improved. Also, these kind of molecules can be vapor deposited and are reasonably thermally stable. So that is an added advantage to these kind of molecules. The aluminum complex also does a little bit of that. It modulates the transfer of electrons, and also in addition to that, if it generates any radiative process, it adds to the efficiency of the whole system if it happens to generate light through the fluorescence process. But generally, if you choose the remaining 3 layers correctly, the aluminum complex just acts as a electron transport layer. Alpha NPD that I didn't mention is a hole transporter. It is the same diamine that we talked about in the simpler design. So it's just another diamine for this kind of design. So this is one complicated design that I just wanted to mention. There are many variations of it. Obviously, these molecules are not a single molecule. In each of this layer, there would be multiple variations of these chemical compounds that can be used for the corresponding application. Apart from that, this arrangement is just an example. That could be even variation in this ordering of the layer based on the HOMO and LUMO of all the components. So this particular combination is based on the energy levels of all the components that we're talking about. If you are going to choose other kinds of hosts and iridium complex, or other kinds of exciton block layer, or other kinds of electron transporter layer or hole transporter layers, then the thickness and variation in order, there may be some tweaking to it so that you get higher and higher efficiency. But mostly the cathode and anode side will mostly remain unchanged. You can simplify the structures by help of molecules, polymers. So other people have tried to make polymers where you have the hole transporter host and the iridium complex stuck at the same polymer. So instead of having to use 2 polymers and coat them together, so this emission layer, the host and iridium are being coated at the same time to the emission layer. Instead of that, you can use polymers that have the amine molecule and the iridium complex stuck to the same polymer. And polymers are, after all, a lot easier or faster to make films out of. There are variations that make use of polymers that are not necessarily conjugated. So keep that in, as an interesting aside as where polymers can help. If you want to read more about it, For polymer OLED, there are different designs. This is again the same picture. It's a more colorful picture of the design. Polymers can have different designs and have different roles in organic LEDs. We can have conjugated polymers with conjugated backbone. Those perform certain functions in polymer organic LEDs. We'll talk about that in a minute. You can have conjugated polymers with pendant groups, like these kind of groups that can also be used in conjunction with the conjugated systems. So there are many complicated designs are made out of polymers, but we'll only look at the conjugated backbone design in a minute, because that was the earlier research done in this field. This one would be an example. This polymer would be an example of this kind of setup, where you have a non-conjugated polymer with pendant group that are functional in nature. For conjugated backbone polymers, the polymer that have been most or earliest studied polymers for organic LEDs are these polyvinylines. They have again have the right band gap, band structure, and homer lumo for LED applications. These polymers can form crystalline films better than some other polymers, especially compared to polythiophene and polyacetylene. These make crystalline films a little bit easier, and they are sometimes better soluble than things like polyacetylene or unsubstituted polythiophenes. So PPV, for the short for that polymer, was the earliest polymer that was used for OLED application. So for OLED application, now we are moving into a device where you have the small molecule light emission layer replaced by polymer light emission emissive layers. So instead of aluminum complex or iridium complex, now we're talking about replacing those molecules with conjugated polymers to make the same device. Other components will more or less be similar to the previous design. For PPV, the synthesis, if you are curious, it is slightly different. We didn't talk about this when we talked about synthesis of conjugated polymers. It's kind of interesting and unusual. Starting material is this, but that is not the final polymer. When you take this kind of molecule and treat it with a base, it undergoes rearrangement reaction that gives to intermediates that then can act as a monomer for polymerization, and then it can polymerize, and then you can eject the remainder of the sulfur group to get to the final conjugated polymer. So it's a slightly unusual and different from other conjugated polymers we talked about. Polyacetylene we did by Ziegler-Natta catalyst, polythiophene by oxidative process, and same with polypyrrole. For PPB, it just has a slightly unusual synthesis process. The PPB band gap is such that the earliest systems are, of course, going to be highly inefficient, but over time, people have come up with more variations in the traditional PPB structures, variation that has electron donating group with some hydrocarbons, and we know that electron donating groups change band gap, that changes color. You can have donating groups and then unusual, really big looking structures. These are actually cholesterol like compounds, not exactly cholesterol, but this is a structure that is very similar to cholesterol. So these cholesterol kind of functional groups, they introduce disorder in the system, and that also changes the band gaps in certain cases. By introducing disorder, you are forcing the gap between neighboring polymer chains to increase. That also changes band gap. Apart from the donor group, because of the oxygen groups, they also change the band gap. And you can put other conjugated groups directly to the backbone. So this is a double bond. It's same PPB, but with more benzene rings. That also drastically changes the band gap, band structure, and the color of the emission light. Bulky substrate, there is something called an effective conjugation length. So, that modulates that. So I didn't want to mention that. And it also modulates how quickly the structure can aggregate and form cluster. So that also plays a part in both the charge carrier mobility and the band gap. So unusual structures can have a drastic effect. Compare that structure to this. So mostly electronic structure wise, they are same, but this three-dimensional cholesterol structure has other property that modulates crystal structure, that changes it in an unusual way. Okay, so other polymers that are used for emissive layer, polyfluorines. So it's not fluorine as in fluorine atom, so it's a different spelling. So this group is called a fluorine. So those kind of polymers are also popular. Substituted polythiophene are also seen. Polyquinolines, we looked at this in the dielectric topic, but quinoline has these kind of fluorescent properties as well. And fluorinated polyethers also have some level of fluorescence, even though they are not actually conjugated polymers. So there are other family of polymers that are also studied for the emission as the emission layer for polymer containing LEDs. In general, polymer containing LEDs have lower efficiency than small molecules ones. So that's why that is the least developed of material for the emission layer of LEDs. There is one more polymer that shows up in literature quite a lot, which is not exactly the emission layer, but this is called a P.PSS, and it is a very popular polymer that shows up in OLED literature. It's just as an aside. It acts as a whole injection layer. It's a different name now. It's not a whole transporter layer. It's whole injection layer. So what this polymer does is it is usually sometimes coated on the indium tin oxide layer. So this is after all a polymer, and it is also very popular. So if it shows up, you need to know why people use it. The reason for using it is, first, it smoothens the indium tin oxide layer, and that helps in injection of the holes on the anode side. And also, because of its polymeric nature and its energy level, the barrier to hole injection is modulated by using P.PSS. So this is an example of a device. So anode, emissive layer. So it is MEHPPV. So this is this compound. So that is the emission layer and the cathode. So in this setup, in this one particular experiment, they found the barrier to hole injection. Hole injection happens on the anode side. The barrier, the overall barrier, measured barrier is 0.2 electron volt. But in the same device, I'm missing the metal, but in the same device, if you put this unusual polymer on the indium tin oxide layer, the barrier is reduced. And mostly it is believed because it smoothens the surface of indium tin oxide, as well as the energy level is such that it makes the transport of hole from the anode to the emission layer a little bit better. So sometimes this kind of polymer shows up in devices or LED devices. I just wanted to mention is what this is. After all, it is also a conjugated polymer, mixture of a conjugated polymer and non-conjugated polymer. So sometimes it's easy to mistake it as the emissive polymer. That is usually not its purpose. The PPV variant is the emissive layer in this case, just as an aside. The other polymer that is used to improve efficiency of blue LED specifically. So blue emission requires high band gap, and that means high band gap meaning the LUMO is going to be higher. Sorry, let me think. Okay, got it. So for blue LEDs, this is for specifically for blue LED. To have the band gap high, because that's what blue emitter is. You have to have HOMO going down in energy. The LUMO also goes down in energy, but not by much. That's why you would increase the band gap. And because of that, there is, since when you try to change band gap and if you change it drastically, the efficiency of injection of hole from indium tin oxide to the HOMO of the emitter, there is a more of a barrier. And because of that, instead of P.PSS, kinds of polymers are also studied, where including these kind of polymers help in the injection of holes further and also increases efficiency. This is also another polymer that shows up in OLED literature, and again, it is not usually used as an emissive layer. It is used for a hole transport layer as well. The problem with this kind of polymer is it's non-conjugated, so it is, after all, a dielectric material as well. It has its limitation, as it requires certain voltages where it can perform its whole injection layers. So these isolated examples of polymers that shows up in OLED literature, I'm just mentioning them, what they look like and what role they play, because it's very often confused as the emission polymer. There are other cross-link variations of that that are also used. The last topic we want to talk about, it's getting a lot of topics. I'll quickly give examples because of its interesting structure, are the topic of white LED. White LEDs, whenever you study LEDs, white LEDs is important because for general lighting, white LED is needed. Traditionally, the easiest way of making white LEDs is to have filters that mix and match the primary colors, or filters that are based either passive filters that filter out RGB in appropriate fashion, or active filters that are fed by blue light and then emit red and green. You can do that to generate the RGB, or have filters that are also active emitters that they absorb fluorescent light and then emit red, green, and blue. And once you have red, green, and blue, you have access to most colors that is required for visualization, and not only for display. If you have all the colors, you can think of white light. So that is the easier way of doing. More roundabout or modern way of doing white light emission is done through choice of polymers. There are complicated systems that emit a single polymer that has blue emitting units. These are polyfluorines having those nitrogen containing groups, and chlorofluorines having another kind of group, and those taken together are blue emitters. You have polyfluorines conjugated to, again, some unusual structures, that are green emitters and red emitters. So this is another way of combining everything in one place. A single polymer having blue emitters, green emitters, and red emitters, as well as groups that modulate the charge carrier mobility in a single polymer. And if you have a single polymer that does all the functions, you wouldn't have to worry about those complicated layer structure where each layer has to be sequentially deposited. So if you can think of polymers that do all the function in one go, that would be a very attractive field of research that people would be interested in. Obviously, the structure is going to be quite complicated, and complicated structures will then require complicated polymerization techniques to make it happen. So in one side, you are cutting down the fabrication steps, and the other side, you are making polymers that are really complicated enough that drawing in a single row is getting difficult. The other strategy, so this is the result of that. The device, the device had the electron transport layer. The whole transport layer is already present, so there is a energy transfer that uses the blue light to modulate the red and greens, and this is the emission. So it has the red, green, and blue light, which are emitted at different ratios, so effectively making white light when taken together. Another strategy is to have block copolymers. So this was random copolymers. Block copolymers made out of all the components together and have the different blocks of the block copolymer do different things at the same time. So what's happening over here? We'll look at the structure. You have, this is essentially a polystyrene, and from the end group, you may realize it is prepared through nitroxide leaving radical polymerization. So these are block copolymers prepared by controlled radical polymerization. They have the whole transport layer, the electron transport layers, an iridium complex that emits red light, an iridium complex that generates blue light. You can see the electronics of the side groups are slightly different. That gives rise to different colors. In this case, you don't want the iridium complex to be intimately mixed in. Unlike in here, where the systems were mixed in and they're working together because of the electron transport layer. In this case, to generate light, you want the blue block of the polymer that has a blue emitter and block of the polymer that has the red emitter to be spatially separated so they can generate blue and red light separately. So because of that, you choose the monomers carefully so that after you make the block copolymer and you have the other groups slightly different so that the two blocks phase separate into two different components, and they phase separate into regions that is predominantly red light emitting region and then the region that are mostly blue light emitting region. And this kind of special rearrangement does one thing: it improves the charge carrier transport, as well as improves the phosphorescence, so that the blue component doesn't contribute or take away from the red component, because these operate through the phosphorescence mechanism. And if they are intimately mixed with each other, they will transfer energy to each other and won't be purely blue or purely white, or they will just feed from each other and use up the energy. So because of that, there are complicated systems that have the blue region and red region separate out, and the driving force for that separation is the choice of the block copolymer that forces the two blocks to phase separate and keep the red emitter away from the blue emitter. That is another strategy of mixing colors and then generating white light. These are a little bit advanced topics that are currently being researched to make white light. Still, the most easiest and convenient approach from a commercial point of view is the use of filters that operate through different mechanisms to generate the RGB light and eventually generate white light. But the goal is to, of course, find better and better polymers that are more efficient at generating multiple colors without interfering with each other, and then externally mixing them and generating white light. Most of the topics I covered are on this is from this review. So if there is any confusion on the topics, you can read this review. I would recommend to read at least how an OLED works from this this review, which I'll share in the shared folder. Even though if you don't go to these topics, at least from this review, at least read what is the basic principle of OLED operation. Okay, so we'll stop here. I don't want to start any new topic, and this is the last class for this course, and tentatively the quiz is on Saturday. If there is any change of plan, I'll have to let you know on the main chat. I'm hoping it doesn't change, but we'll have to wait and watch.